Few scientists have shaped our understanding of reality as profoundly as Erwin Schrödinger. A pioneer of quantum mechanics, he formulated the wave equation, a mathematical breakthrough that became one of the cornerstones of modern physics. His work helped explain the behavior of electrons, the structure of atoms, and the strange, counterintuitive laws that govern the microscopic world. Yet Schrödinger was not just a physicist, he was a thinker who questioned the very foundations of science. His famous Schrödinger's cat paradox remains one of the most debated concepts in quantum mechanics, challenging our perception of observation, probability, and existence itself. But his impact didn't stop there. His interdisciplinary approach led him to explore the mysteries of biology, philosophy, and the nature of consciousness, inspiring future generations of scientists. His life, however, was as unconventional as his theories. From academic triumphs to intellectual conflicts, from fleeing political turmoil to reshaping entire scientific fields, Schrödinger's journey was one of discovery, defiance, and relentless curiosity. This is the story of Erwin Schrödinger, the physicist who dared to challenge reality and, in doing so, changed science forever. In the heart of Vienna, Austria, on August 12, 1887, Erwin Schrödinger was born into an intellectually stimulating household. His father, Rudolf Schrödinger, was a respected botanist, and his mother, Georgine, came from a well-educated family. This rich intellectual environment nurtured young Erwin's curiosity, fostering an early fascination with the natural world. Unlike most children his age, he showed a remarkable ability to grasp abstract concepts and solve complex problems. Growing up in a bilingual household where both German and English were spoken, Erwin developed a strong linguistic ability that would later aid his academic pursuits. His education began at home, where his father introduced him to a broad spectrum of scientific disciplines, from chemistry to physics. However, it was mathematics and physics that captivated him the most. Numbers, formulas, and physical principles seemed less like rigid rules and more like an elegant language describing the universe. Schrödinger's formal schooling took place at the Akademisches Gymnasium in Vienna, one of the most prestigious schools in the city. There, he excelled in mathematics and physics, often outperforming his peers. He was not only a disciplined student but also one deeply introspective, drawn to philosophy as well as science. He admired the works of German philosophers such as Schopenhauer, whose ideas about the nature of reality and consciousness would later influence his scientific perspectives. By the time he reached adolescence, his path seemed clear. Encouraged by his intellectual environment, his natural curiosity, and his exceptional abilities, Schrödinger set his sights on the study of physics. The vibrant scientific culture of early 20th century Vienna was an ideal setting for an aspiring physicist. In 1906, he took his next significant step, enrolling at the University of Vienna, where his formal journey into the depths of theoretical physics would begin. Before we dive into Schrödinger's early academic journey, please like, subscribe, and hit the notification bell to catch every detail of this incredible story. Share in the comments what impressed you most about his childhood and education. In 1906, Erwin Schrödinger entered the University of Vienna, a prestigious institution that had already produced some of the greatest scientific minds of the time. Immersed in an environment of rigorous intellectual pursuit, he quickly distinguished himself as a gifted and diligent student. The university's physics program emphasized both experimental and theoretical work, but Schrödinger gravitated toward theory, drawn to its elegance and the power of mathematical abstraction. One of the most influential figures in his academic development was Friedrich Hasen-Earl, a brilliant physicist who had contributed to early discussions on energy and relativity. Under Hasen-Earl's guidance, Schrödinger refined his mathematical skills and deepened his understanding of the fundamental principles of physics. His studies covered classical mechanics, thermodynamics, and electromagnetism, but it was the emerging field of quantum theory that would soon capture his imagination. During these formative years, Schrödinger became increasingly aware of the revolution taking place in physics. Max Planck's quantum hypothesis, which suggested that energy was quantized, had already begun reshaping scientific thought. Albert Einstein's groundbreaking work on the photoelectric effect further challenged classical understandings of light and matter. These radical ideas intrigued Schrödinger, setting the stage for his later contributions to quantum mechanics. By 1910, he had completed his doctoral dissertation, focusing on the study of electrical conduction on the surface of insulators. His work demonstrated his ability to blend mathematical rigor with physical intuition, a skill that would define his later breakthroughs. Shortly after earning his doctorate, he remained at the university as an assistant to Franz Exner, where he continued his research while mentoring younger students. However, his promising academic journey was soon interrupted by global events. In 1914, World War I erupted, and like many young scholars of his time, Schrödinger was drawn into military service. He served as an artillery officer in the Austro-Hungarian army, an experience that, while not halting his intellectual pursuits entirely, marked a significant detour in his career. Despite the disruptions of war, Schrödinger's deep fascination with physics remained unwavering. When he returned to academia after the war, the scientific landscape had changed dramatically. Quantum mechanics was on the rise, and Schrödinger was ready to take his place at the forefront of this revolutionary movement. After the turbulence of World War I, Erwin Schrödinger resumed his academic career, eager to reconnect with the scientific community. The war had disrupted not only his life, but also the progress of physics in Europe. However, the post-war period brought a renewed energy to scientific inquiry, and Schrödinger was determined to establish himself as a leading figure in theoretical physics. In 1920, he secured a position at the University of Jena, a small but respected institution in Germany. Though his tenure there was brief, it marked the beginning of his independent academic career. The intellectual atmosphere was stimulating, but resources were limited, and the university lacked the prestige of Vienna. Nevertheless, Schrödinger made significant strides in his research, exploring problems related to atomic structure and the behavior of electrons. Recognizing greater opportunities elsewhere, he soon moved to the University of Stuttgart and later to the University of Breslau. During this time, he began engaging with some of the most pressing questions in physics. The Bohr model of the atom, introduced in 1913, had provided a partial understanding of atomic spectra, but fundamental mysteries remained unresolved. Schrödinger became increasingly interested in the wave-like behavior of matter, an idea that was gaining traction among physicists. By 1921, Schrödinger's reputation had grown, earning him a position at the University of Zurich, where he would spend several of the most productive years of his career. Zurich provided him with an intellectually rich environment, surrounded by brilliant minds who were actively debating the latest developments in quantum theory. During this period, he encountered the groundbreaking ideas of Louis de Broglie, who had proposed that electrons exhibited wave-like properties. This concept resonated deeply with Schrödinger, who saw in it a more intuitive approach to quantum mechanics than the probabilistic framework emerging from Werner Heisenberg's matrix mechanics. As he immersed himself in these ideas, Schrödinger began formulating what would become one of the most profound equations in physics. However, the path to discovery was not without obstacles. The field was deeply divided, and the debate over how to interpret quantum phenomena was intensifying. Unfazed by these challenges, Schrödinger pressed forward, seeking a new mathematical formulation that could unify the behavior of particles and waves. His breakthrough was imminent. The following years would not only define his legacy, but also reshape the very foundations of modern physics. At the University of Zurich, Schrödinger found himself in an environment conducive to deep intellectual exploration. The early 1920s were a time of great transformation in physics, with the classical Newtonian worldview being challenged by the emerging field of quantum mechanics. Inspired by de Broglie's hypothesis that particles exhibited wave-like properties, Schrödinger began to explore new mathematical frameworks to describe atomic behavior. He was particularly intrigued by the limitations of the Bohr model, which, despite its successes, relied on somewhat artificial assumptions about electron orbits. Schrödinger believed that a more natural and continuous description of electron motion was possible. He turned to wave theory, suspecting that atoms might be better understood not as rigid mechanical systems, but as entities governed by wave-like behavior. Between 1924 and 1925, he intensively studied the works of other physicists, including Max Planck and Albert Einstein, who had both contributed to the understanding of quantized energy. Einstein, in particular, had extended de Broglie's wave-particle duality ideas, suggesting that they might apply to more than just photons. Encouraged by these ideas, Schrödinger sought a mathematical formulation that could describe the behavior of electrons in atoms in a wave-like manner. He began developing a new theoretical approach, one based on differential equations rather than the matrix mechanics approach pioneered by Werner Heisenberg. Schrödinger found Heisenberg's formulation mathematically opaque and conceptually unsatisfying. He was convinced that an alternative description of quantum mechanics could be derived, one that was both mathematically elegant and physically intuitive. His work during this period resulted in a series of groundbreaking papers that laid the foundation for wave mechanics. By mid-1925, he had made significant progress in constructing a wave equation that could describe the quantum state of an electron. Unlike previous models, Schrödinger's approach treated electrons not as discrete particles jumping between orbits, but as continuous wave functions evolving over time. This was a profound shift in perspective. Rather than imagining electrons as tiny planets orbiting a nucleus, Schrödinger proposed that they behaved like standing waves, with their positions described probabilistically rather than deterministically. This idea, though radical, was elegant and offered a new way to visualize the atomic world. Schrödinger was on the verge of unveiling one of the most important equations in the history of physics. The next phase of his work would not only define his career but also revolutionize the understanding of quantum mechanics forever. In 1926, Erwin Schrödinger published a series of groundbreaking papers that introduced what would become one of the most fundamental equations in physics, the Schrödinger equation. This equation, which describes how quantum states evolve over time, provided a powerful and elegant mathematical framework for understanding the behavior of electrons and other subatomic particles. Schrödinger's approach was rooted in wave mechanics, a stark contrast to the matrix mechanics developed by Werner Heisenberg. While Heisenberg's method relied on abstract algebraic formulations, Schrödinger's equation described particles as wave-like entities, governed by a continuous function known as the wave function, pas. This function, when squared, represented the probability of finding a particle in a particular location, a concept that would later become central to quantum mechanics. The time-independent Schrödinger equation, derived from classical energy principles, successfully described the behavior of electrons in atoms. It explained why electrons occupied discrete energy levels, a phenomenon previously observed in spectral lines, but not fully understood. Schrödinger's work provided a direct, mathematically rigorous explanation for atomic structure, surpassing the Bohr model's limitations. His equation also had profound implications beyond atomic physics. It could be applied to molecules, solid-state systems, and even quantum field theory. Physicists soon recognized its universal applicability, and Schrödinger's wave mechanics quickly gained acceptance as a powerful tool for solving quantum problems. Despite the equation's success, Schrödinger himself remained uneasy about its interpretation. He initially hoped that wave mechanics could restore a deterministic view of nature, eliminating the probabilistic aspects introduced by quantum mechanics. However, the Copenhagen interpretation, championed by Niels Bohr and Heisenberg, argued that quantum mechanics was inherently probabilistic, an idea Schrödinger struggled to accept. Nevertheless, his equation had reshaped physics. It provided a conceptual and computational foundation that is still used today in fields ranging from chemistry to quantum computing. Schrödinger's work had ushered in a new era in science, but his quest to understand the true nature of quantum reality was far from over. Soon he would propose a thought experiment that would challenge the very foundations of quantum interpretation, the famous Schrödinger's cat paradox. By the mid-1930s, quantum mechanics had become one of the most successful scientific theories, yet its interpretation remained deeply controversial. The Copenhagen interpretation, led by Niels Bohr and Werner Heisenberg, suggested that quantum systems existed in a superposition of states until observed, at which point the wave function collapsed into a definite state. This view, though widely accepted, troubled Schrödinger. He saw it as an incomplete and unsatisfactory description of reality. In 1935, seeking to illustrate the paradoxical nature of quantum mechanics, Schrödinger devised one of the most famous thought experiments in scientific history, Schrödinger's cat. The experiment was purely conceptual but highlighted a profound issue in quantum interpretation. Schrödinger imagined a sealed box containing a cat, a radioactive atom, a Geiger counter, and a vial of poison. The setup was designed so that if the radioactive atom decayed, the counter would trigger the release of poison, killing the cat. However, according to quantum mechanics, the atom's decay was governed by probability, existing in a superposition of decayed and undecayed states until observed. By extension, the cat, linked to this quantum event, would also be in a superposition, both alive and dead simultaneously, until the box was opened and an observation was made. The absurdity of this scenario was intentional. Schrödinger wanted to challenge the idea that quantum mechanics, as understood through the Copenhagen interpretation, could be applied uncritically to macroscopic objects. He did not suggest that cats could actually be in such states, but rather that the standard interpretation led to paradoxical conclusions when scaled up to everyday objects. His thought experiment ignited intense debate. While Bohr and his followers maintained that observation was a fundamental part of quantum reality, others, including Einstein, shared Schrödinger's discomfort with the probabilistic nature of the theory. The paradox inspired alternative interpretations of quantum mechanics, including the many-worlds interpretation, which suggests that all possible outcomes of a quantum event occur in parallel universes. Schrödinger's cat remains one of the most famous symbols of quantum mechanics, encapsulating the mystery and counterintuitive nature of the microscopic world. While Schrödinger himself never fully resolved his concerns, his thought experiment profoundly influenced the philosophical and scientific discourse surrounding quantum mechanics. Despite these conceptual struggles, Schrödinger's work had already cemented his place in history. However, his career would soon face unexpected challenges, not from physics but from the political and social upheavals of the 20th century. As the 1930s progressed, Erwin Schrödinger found himself increasingly at odds with the prevailing trends in quantum mechanics. His dissatisfaction with the Copenhagen interpretation placed him in philosophical conflict with figures like Niels Bohr and Werner Heisenberg. Schrödinger, much like Albert Einstein, believed that quantum mechanics should offer a more complete, deterministic explanation of nature, rather than rely on probabilities and wave function collapses. But while scientific debates were one source of tension, political turmoil soon became a far more immediate threat. The rise of Nazi Germany and its influence over Austria placed Schrödinger, like many intellectuals, in a precarious position. Though he was not Jewish, he openly opposed the Nazi regime's oppressive policies and its intrusion into academia. In 1933, when Hitler rose to power, Schrödinger made a bold decision. He resigned from his position at the University of Berlin, unwilling to work under a government that was purging Jewish scientists and restricting intellectual freedom. That same year, Schrödinger was awarded the Nobel Prize in Physics, sharing the honor with Paul Dirac. The award recognized his foundational contributions to wave mechanics, cementing his status as one of the most important physicists of the 20th century. Despite this triumph, his personal and professional life remained in upheaval. In 1938, when Austria was annexed by Nazi Germany, Anschluss, Schrödinger found himself in grave danger. Although he had previously attempted to remain neutral and even signed a letter of loyalty to the Nazi regime to protect himself, his past criticisms of Hitler's government resurfaced. Fearing for his safety, he fled Austria with his family, leaving behind his homeland and much of his previous life. His exile led him on a journey across Europe. He spent time in Italy, the United Kingdom, and eventually Ireland, where he accepted an academic position at the newly established Institute for Advanced Studies in Dublin. Here, away from the political chaos of continental Europe, he was able to rebuild his scientific career. Despite the challenges he had faced, Schrödinger remained intellectually active. In Dublin, he began exploring new fields, including biology, and wrote extensively on the philosophical implications of quantum mechanics. His scientific journey was far from over, but the war years had left a lasting impact on his life and worldview. Settling in Dublin, Ireland in 1939, Erwin Schrödinger embarked on a new intellectual chapter. At the Dublin Institute for Advanced Studies, he found an environment that allowed him to pursue scientific inquiry with a level of freedom he had lost in Nazi-controlled Europe. Though quantum mechanics remained a central theme in his work, he also began exploring a broader range of ideas, particularly in philosophy and biology. During this period, Schrödinger wrote one of his most influential works outside of physics, What is Life? 1944. In this book, he applied principles of quantum mechanics and thermodynamics to biological systems, proposing that genetic information was stored in an aperiodic crystal, a strikingly prescient idea that foreshadowed the discovery of DNA as the carrier of genetic information. His work inspired physicists such as Francis Crick, who later co-discovered the structure of DNA, highlighting Schrödinger's impact beyond quantum mechanics. Despite his growing interest in interdisciplinary science, he never abandoned his concerns about the interpretation of quantum mechanics. He remained skeptical of the probabilistic nature of the Copenhagen interpretation and continued advocating for a deterministic understanding of reality. His philosophical writings reflected a lifelong quest to reconcile quantum physics with a coherent view of the universe. As the years passed, Schrödinger maintained an active role in academia, but he longed to return to Austria. In 1956, after nearly 2 decades in exile, he was finally able to return to Vienna, taking up a professorship at the University of Vienna. Though he was welcomed as one of Austria's greatest scientific minds, he found that the world of physics had evolved significantly since his departure. The rise of quantum field theory and new experimental discoveries had taken physics in directions he had not anticipated. In his later years, Schrödinger continued to write on both physics and philosophy, seeking a deeper understanding of reality that extended beyond conventional scientific frameworks. He remained intellectually restless, grappling with profound questions about the nature of existence, consciousness, and the limits of human knowledge. By the time he passed away in 1961, Schrödinger had left behind not only a body of work that revolutionized physics but also a legacy of intellectual courage, one that defied both scientific orthodoxy and political oppression. Erwin Schrödinger's contributions to physics extended far beyond his own lifetime. His wave equation, formulated in 1926, remains one of the most important mathematical tools in quantum mechanics, governing everything from atomic interactions to modern technological applications. His work provided theoretical foundations for quantum chemistry, semiconductor physics, and even quantum computing, shaping the very fabric of modern science. One of the most profound impacts of Schrödinger's equation was its role in quantum chemistry. By describing how electrons behave in atoms and molecules, it became an essential tool for understanding chemical bonding. Today, computational chemists use Schrödinger's wave mechanics to predict molecular structures, enabling advancements in materials science, pharmaceuticals, and nanotechnology. His ideas also laid the groundwork for semiconductor physics, the field that led to the development of transistors and modern electronics. Without the principles of quantum mechanics, technologies such as microprocessors, lasers, and MRI machines would not exist. Schrödinger's work indirectly contributed to these breakthroughs, as his equation became a fundamental tool for engineers and physicists designing electronic devices. Beyond applied physics, Schrödinger's philosophical and conceptual impact continues to resonate. His famous Schrödinger's cat paradox remains a central reference in discussions about quantum interpretation, consciousness, and the nature of reality. His skepticism toward the Copenhagen interpretation inspired alternative theories, including the many worlds interpretation and hidden variable theories, which remain subjects of intense debate among physicists. Additionally, his interdisciplinary thinking influenced fields outside of physics. His book, What is Life? inspired generations of biologists, including James Watson and Francis Crick, who later cited Schrödinger's ideas as instrumental in their discovery of the double helix structure of DNA. In this way, Schrödinger's vision extended beyond quantum mechanics, shaping the very foundation of modern genetics. Though he remained philosophically conflicted about quantum mechanics throughout his life, Schrödinger's contributions became indispensable to modern physics and technology. His name is forever enshrined in scientific history, not only through the Schrödinger equation but also through his lasting influence on the intellectual and technological revolutions of the 20th and 21st centuries. His work was not just theoretical, it was a blueprint for the future, a future in which quantum mechanics continues to drive innovation in ways even Schrödinger himself could not have fully imagined. More than half a century after his passing, Erwin Schrödinger's influence on science and philosophy remains profound. His wave equation, one of the pillars of quantum mechanics, continues to be used in fields ranging from particle physics to material science, guiding new discoveries in both fundamental and applied physics. One of the most exciting modern applications of Schrödinger's work is in quantum computing. Unlike classical computers, which use bits that exist in either a 0 or 1 state, quantum computers exploit superposition and entanglement, principles deeply rooted in the Schrödinger equation. The race to develop practical quantum computers, capable of solving problems beyond the reach of classical machines, is a direct testament to the power of the mathematical framework Schrödinger helped establish. His famous Schrödinger's cat paradox remains central to discussions about the foundations of quantum mechanics. The paradox continues to inspire new interpretations of reality, such as the many worlds interpretation, which suggests that all possible outcomes of a quantum event occur in separate, parallel universes. Meanwhile, advancements in quantum entanglement and measurement theory have pushed scientists to reconsider the nature of observation, furthering Schrödinger's legacy in debates about the fundamental nature of reality. Beyond physics, Schrödinger's interdisciplinary thinking has had a lasting impact. His book, What is Life?, continues to be influential in biophysics and systems biology, with researchers exploring quantum effects in biological processes such as photosynthesis, enzyme reactions, and even the mechanics of consciousness. His vision of a unified scientific approach, bridging physics and biology, remains an inspiration for modern researchers seeking to unravel the mysteries of life at the quantum level. Philosophically, Schrödinger's lifelong quest for a deeper understanding of reality still resonates. He challenged the orthodox views of quantum mechanics, pushing for alternative ways to comprehend the quantum world. His concerns about determinism, wave function collapse, and the role of the observer continue to spark new theories, ensuring that his work is not just a historical artifact but an active part of contemporary scientific discourse. Even outside of academia, Schrödinger's name has permeated popular culture. Schrödinger's cat has become a metaphor for paradoxes, uncertainty, and the strange nature of reality, referenced in literature, television, film, and even everyday conversations about probability and decision-making. His ideas have reached audiences far beyond the scientific community, making him one of the most recognizable figures in modern physics. Schrödinger passed away in 1961, but his legacy is timeless. His work remains a cornerstone of quantum theory. His paradox continues to challenge our understanding of reality, and his visionary insights inspire new generations of scientists. As quantum mechanics continues to evolve, Schrödinger's influence will undoubtedly shape its future, ensuring that his name remains synonymous with the deepest mysteries of the universe.